Hey everyone, thank you for joining us today for the technical forum under Konveyor. We have three different topics today that we want to go over. So we're going to talk a little bit about persistent volume copying and change that allows us to handle changing ownership and permissions. Then we're going to talk a little bit about some work that's been done to improve how we release plugins in the Crane project. And then we will end talking about some new R&D work we're doing. We're exploring using Crane to migrate VMs with KubeVirt. So with that, we will get started where Pranav will talk to us about some of the PV copying work that he's doing. Pranav, all you.
Yep. Can everyone see my screen? Okay.
Yep.
Okay. Earlier this month, we accepted an enhancement in the Konveyor enhancement repository, which talks about managing file ownership of files transferred via rsync in Crane, and then making Crane usage possible, the state transfer usage possible for non-admin users. Today, we'll talk about go over that enhancement and yeah. So a little bit of background about the problem. MTC transfers. MTC uses the same state transfer library that Crane uses, and by default, it runs rsync pod as root. That is because MTC migrates the namespace definitions from source to destination namespace as is. And there's a thing called UID ranges on OpenShift that OpenShift, whenever you create a namespace, OpenShift assigns a unique UID range to the namespace. So any pod that runs in that namespace and it's not running with explicit UIDs, it will be assigned a UID from that range that's assigned to the namespace. And MTC, when it migrates from source to destination, it doesn't change these values. So on the destination, the UID ranges are exactly the same as that of the source. And as a result, MTC has to preserve the file ownership information of the migrated files. And that's why it also has to run rsync pod as root. Here's an example on the screen. On the left-hand side, we have a source namespace, and on the right side, we have a target namespace, which is migrated by MTC. And as you can see, we have the exact same UID ranges and supplemental groups assigned. And that's part of the reason why we need to preserve ownership information when transferring files. If we don't preserve that info, the application won't be able to access the file because of the UID range mismatch. Now, since rsync pod is running as root, there are some things that we need to do for the pod to be admitted. So one of the things is that the user needs to be an admin, or custom SCC must be created by an admin user, and the user who is running rsync pod needs use access to that SCC. And that SCC should allow all the capabilities that the rsync pod uses. So essentially, it's basically elevating your privileges. MTC basically uses this approach in that operator goes and creates a custom SCC called rsync any UID. That SCC allows running rsync pod with 0 UID root. And yeah, next up. So what are some problems that that are presented because of this approach in Crane? The first thing is that Crane assumes that the namespaces are created in the destination cluster prior to migration. What it means is that the namespace definition is not migrated by Crane. And since a new namespace is created in destination, The UID range assigned to that namespace in OpenShift will not be the same as source. And as a result, the files cannot be owned by the same users, same UID GIDs that represent on the source. This is exactly opposite of what MTC assumes. It assumes that the namespaces are same, so files, the UID GIDs on the files will be same. But this is not true for Crane because namespace is most likely going to have a different UID than the source. Second problem is that Crane is not designed for cluster admins like MTC is. Crane is designed for app owners. So app owners don't necessarily have admin privileges. They may or may not be able to create privileged pods. The thing that MTC does by creating a custom SCC does not apply to Crane. You can still argue that you can still create an SCC, but that's something a cluster admin is supposed to do for every app owner, and in the process they're also elevating their privileges. So we can't do that for Crane. And as a result, we need a generic solution for this problem such that even the least privileged users can use state transfer. As I explained in the first slide, since Crane assumes that a new namespace is created in the destination, OpenShift will assign another unique UID that may or may not be the same as the source. So we don't really need to care about owners and groups. We don't need to preserve that information during state transfer, which is what MTC does. But for Crane, it's not a requirement, because if you do that, you are still running into the same problem. You cannot guarantee that the apps will be able to use the files because the UIDs will be different. And then the second problem is that app owners cannot run privileged pod. So let's take a look at how rsync preserves file permissions. So it reads file on the source, it transfers it to the destination, then it writes file on the destination, and when the file is written, it's written using the UID and GID of the process that's running rsync. In case of MTC, since this is a root user, the files will be owned by root users, and I think the GID is 0 as well for the root user. And since we want to preserve permissions, this is just for MTC. Since we preserve permissions, it will basically run a chown operation to change the owner's groups back to what was there on the source. So this is where we require rsync pod to be privileged. This is the only step in the entire process that requires us to run a privileged pod. But since we don't need to change the permissions, we can basically ignore this step. We can remove that. So that can be done by simply removing the user and group options. These options are present in the archive flag in rsync. So basically just getting rid of that, we are asking rsync not to run chown. Then how would that work? So again, same process, read file on the source, transfer to destination, and write file on the destination. But there's a caveat to writing the file. Now, since we are not running a privileged pod, we need file returned to the destination using the right UIDs and GIDs. And for that, we will make use of SCC capabilities. So the solution here is that rsync pod will use the restricted SCC on OpenShift. So first advantage is that all users have access to restricted SCC. So even a non-admin user can run rsync. With restricted SCC, we don't want privileged pods. We cannot launch privileged pods, but we don't want it because we are not running chown. Restricted SCC provides us with everything that rsync needs except the chown thing. And that's not a problem for us anymore. Uh, and when you assign restricted SCC on OpenShift to a pod, or when the pod gets, so you cannot really assign an SCC. The pod has to get admitted via the right SCC, and when that happens, the UID and the GID of the pod is automatically set to the right range that's assigned to the namespace. That's because restricted SCC users must run as range for the UID. And as a result, our sync will run with the right UID in the destination cluster. So how will our sync work is that, again, the same process: read file, transfer to destination, and write file. When writing the file, since our sync is using the UID that's inherited from the namespace definition because of the SCC, the files will be already owned by the UIDs from the range. So any application that uses those files will be able to access it because they belong to the same range that's assigned to the namespace. And that's it. So you don't need to run ch1 after that. And to do that, we basically remove user and group options from our sync. There are some caveats to this. The first one is that we are assuming that we can use restricted SCC, which will give us these capabilities. It can happen that users may have different SCCs or conflicting SCCs that may interfere with the pod operation, but this is kind of a problem that cannot be solved in a generic way, and it needs to be handled on a case-by-case basis. But on most OpenShift clusters, restricted SCC is the default one and provides the right capabilities. There could be the second problem is that there could be applications that may not strictly use the UIDs that are assigned by the namespace range. And so, for example, you can have a shared storage, which is configured via supplemental groups, and applications may be using that. To solve this, Crane will provide options to the user where they can go and specify the right UID, GIDs they want. And this will be on a per PV basis. They can do it for each and every PV they transfer. So that's all I had for today. I have some reference links put up here. The enhancement doc talks about all these things in detail. One thing that I didn't cover in the slides is that is the pod security on Kubernetes. So when you transfer files from Kubernetes to OpenShift, so the enhancement talks about pod security admission in more detail. Then there's an article that talks about the issues that we ran into because of preserving UID ranges in MTC.
Cool. Thank you, Pranav. Anyone have any questions for Pranav? All right. So next up, Jaydip is going to talk to us a little bit about some of the work that's been done to help out on improving how we improve the release process for on Crane plugins. Jaydip, all you.
Yep. Yep. So today I'm going to discuss around what was the initial implementation that we did around plugin release, why the redesign was needed, what were the improvements made, and how now the process is simpler or better than the previous one. So the problem existed around having too many many manual steps and interventions that uh, leave the whole release process more prone to human error. There were uh, so we discovered that there can be less number of changes that can have the same effect, and we will learn about how we reduce those needed changes and complexities in the later part of the slides. So let's go through some overview. We'll learn about differences of initial and redesigned release process, motivation and improvements that were needed for the redesign, differences in the approaches, and then what are the actual high level changes that goes uh, through several or our central plugin repositories when every plugin is released. So earlier, when an author or plugin author triggers the GitHub action that results in the release of a plugin, the automated process builds and plugins public plugin binary and URL, and then our automated process used to raise a PR against our central crane plugin repository, and adds a manifest and an index file there. Now, the next step would involve manually verifying that uh, PR, and manually verifying URLs and index files entry to particular manifest file of a released plugin, and then merge it in the main branch. Now, initially we thought that we would kind of have two different branches. One is main branch, where everything latest or every released plugin is there, and then we would as and when after testing, we would release those manifest into another branch to just make sure that newly released plugin works as expected, and then that would involve manually raising PR against the branch that was Crane CLI at the time we decided, with all the changes, and then verify the changes. That those changes would involve updating index file, as the new branch would have a new location for respective plugin manifest files. I know this is a really kind of confusing, but we'll learn about the repository structure and how those changes were needed. So this was there in the first draft of or first implementation of plugin release. And then we kind of looked at the process, and we thought that making changes or bringing changes into Crane CLI branch is just an additional step. What we can do is we can have the plugin author responsible for the releasing of the plugin, because releasing of the plugin is basically making it available for use. So we should test everything before we do that. And that is why we decided that all the changes or all the information that is there in the main branch is sufficient enough, and we should only release the plugin whenever it is working as expected and is fully tested. So that kind of reduces the steps of bringing the changes over to Crane CLI and some manual processes, as the final step is just to get the plugins into uh, the main branch rather than Crane CLI branch. So, and this is basically a high level change that we can see right now that reduced the step. But now we'll see what are the some lower level improvements that we made. So again, the motivation was that one was that we had an additional branch that was our intended destination, which is Crane CLI branch, where manual steps were involved in order to get the changes there. And then for every, so initial approach had creating every manifest for a respective version, which meant that we had to update our index file for every uh, new version of a plugin released, and which we figured out on a later part that can uh, be reduced to not changing that index file, and we'll see that also how. So in order to make those changes, we decided initially so in order to make those changes, we decided that our main branch would be the final destination, and then we decided to restructure how our manifest where would look like. And initially, um, so this was the plugin manifest before, where each and individual version would have its own um, respective plugins. So let's say we have three versions of OpenShift, then there would be three manifest files within OpenShift, which would be named as OpenShift 1.0.yaml, OpenShift 1.1.yaml, OpenShift 1.2.yaml, and so on. But now in the redesigned structure, we decided that we would have only one manifest file respective to a plugin and include all the version information, just as you can see right here in that same manifest file. That meant that whenever releasing a new plugin or new version of the existing plugin, we would only have to append the new released information to the existing manifest file. Now, earlier we used to have a map in the index as the index file, which basically had the entries of respective plugin with versions and location of the manifest file. So OpenShift plugin version 0.0.1 and respective URL of that manifest file. 0.0.2 respective URL. So that would mean that with every new version released, we would be adding a new YAML file and we would be updating index. But now as we go and have the array of versions included in the index file, manifest file of a plugin, we only need to update the index as and when we are releasing a new plugin, not the new version. So in the later part, now the current implementation is we have plugins array in the index file, which is basically a name and the location of a manifest file for a particular plugin. And then in the restructure of the repository would look like for every plugin, we only have one index file, where we used to have multiple uh, manifest YAML files, as we required we used to have one-to-one mapping towards the manifest file and the existing version. So the overall repository now looks much simpler than it used to before. And now let's I'm sorry now let's understand what were the what are now the actual changes that go through in terms of YAMLs and code for each plugin release. So while releasing a plugin, if it's a new version, then we can assume that there is a entry in the index file itself. So we don't have to update the index. Rather, we just have to append the information of the latest version and latest release into the existing plugin manifest file, and then raise a PR against current plugins. But if it's a new plugin, then we have to append the location. So first we have to create a manifest file in the respective location, and then we also have to append the location of this newly created manifest into our index file. So that's actually much simpler, or let's say less hurdle than adding a location in the index file every time a new version is released. So that's how we reduced one change, and that it looks like a one change, but in a long run, this is much simpler to uh, maintain, as we are not making any unnecessary changes than needed. And that's all we did in terms of redesigning on a higher level. But I have some reference links over here which are, and we can I mean, you guys can look at initial approach of the plugin release and then redesigned approach. And the other links include the central repository that we have as a Crane plugins, and rest of the plugins that we have released. And then we consume this Crane plugins in Crane plugin manager, which actually is a part of Crane CLI that helps list and add and remove plugins. And that's it. Any questions?
Okay. Thank you, Jaydip. And next up, David is going to talk to us about some of the work that he's been doing using Crane to help migrate VMs with KubeVirt. David, all yours.
All right, let's see if I can manage this. All right, so the way that I want to go about this is I'm going to show a quick demo of what we were doing in this proof of concept. And then once we've done that, then I'll kind of talk through some of the stuff that, some of the hacks that needed to happen in order to make that proof of concept work. And then how we would move forward. So let's just kind of talk through it. So I'm gonna go ahead and talk over it instead of just playing the video. So in order to set this up, I used the MIG agnostic D. I needed the worker nodes to be the metal type. So I'm going to work on updating some of our like documentation to explain how to set up a cluster for CNV. That was one of the big things. But what I ended up doing was creating 2 clusters of OpenShift 4.10 and installed CNV in both of them. And in the first cluster, what I did was I created a virtual machine. And one of the things I had to do was I had to make sure that this virtual machine used a PVC of the same name and that it had a volume mode of type file system. So as of right now, the transfer PVC can't handle block storage. So we had to force the VM to use file system storage. So the next step, making sure I'm not paused. The next step is for me to hop into the console and to jump in there and add something meaningful. This is where I just full screen. Okay. So I log in as the cloud user, and one thing I could do is just play this faster. So I log in and I create some kind of fake data. I call it precious data, and I just fill it with hello world. And now on the destination cluster, what I do is I installed OpenShift pipelines, and I created a pipeline using our Crane runner type stuff. And this is where you see I'm showing off the actual pipeline. What it does is we have 2 threads in this pipeline. The first is to stop the VM and transfer the PVC. And the second thread is where we export the manifests, we transform them, and we apply the transforms, and we create the customization YAML, and then we apply it into the cluster to bring the workload over. This is the simple part where we're just running the pipeline. So I have to give it the source context, the namespace that we're migrating from or we're importing from, the destination context. So you see here, I have a kubeconfig with a secret, and it's referencing the kubeconfig secret. And in that secret is just the kubeconfig with both of these contexts defined. The shared data is a scratchpad that we use for all of these tasks that run in the pipeline. And then once I hit the run button, I can kind of talk through what's happening with Tecton. So a lot of what we're doing with the MTRHO or this crane effort is we're relying a lot on Tecton and the pipeline automation that they provide. So right now we're in the pipeline GUI, and we create a pipeline run is an instantiation of a pipeline. A pipeline includes a bunch of steps, a bunch of tasks. Those tasks, when those tasks are instantiated as task runs, and those each of those task runs has a pod that executes in the cluster. So if you're not familiar with export, it's reaching out to the Discovery API on the source cluster to see all the resources that exist in the namespace. The stop VM was an example task that we created just for this POC that just patches the virtual machine on the source cluster to tell it to shut down. That is a mock or simple example of us quieting the stuff on the source cluster to prevent new data from being written to the PVC. The transform step, what we're doing there is we're whiting out all the things. So an example would be a virtual machine owns a bunch of resources. It owns the virtual machine instance. It owns the persistent volume claim. It has a data volume and a bunch of other resources that it's owned. So we white those out. The only transform that survives here is the transform for the virtual machine. So I said earlier that we used a PVC that had the same name as the virtual machine. And this is where I modified one of our plugins so that when it saw a virtual machine, it would remove the data volume template from the virtual machine spec, and it would update the virtual machine template to include the PVC that's being migrated in the transfer PVC step. So we bring over the virtual machine resource that points directly to the PVC that we've transferred, and then start the virtual machine. Apply. So in the transform step where we create a bunch of JSON patches, what we're doing in the apply step is we're taking the exported resources, that's the raw YAML. So that'll include all of the metadata, all the status, everything, managed fields, takes the transforms that are JSON patches or whiteouts, and it apply step gives you a net new set of Kubernetes manifests that you can use. The idea being that we're stripping out as much cluster specific information as possible. Customize init is essentially what we're doing is we're creating a customized overlay that can be used. You could take this, you could push it to GitHub, and you could create multiple overlays to build on top of this. You could, in this case, what we're using customize to do is to inject some cluster specific information. In this case, the namespace where we're going to deploy this virtual machine. So we use customize to set the namespace. Transfer PVC takes the longest. It took a really long time for that to run. But once that's complete and the PVC exists on the destination cluster, we would apply the resources. And then in the end, what we do is we show that it kind of worked. Actually, it did work. The VM was running and all was great. But what I wanted to talk to was some of the changes that were required. A couple of the things that we learned from this lesson was that we needed to be able to handle some of the SCC when we do transfer PVC. And in our specific example with the virtual machine, is there a specific SCC that the KubeVirt uses to allow the virtual machine or the Virt launcher to execute these VMs and access the files or the block storage in a PVC. So we needed a way in Crane to specify, hey, apply this SCC or these security contexts to the pods that you create in the source and destination cluster in order to run the transfer PVC. So there are a couple of things like that. Let's see if I can show one of those tabs. So in transfer PVC, we also added, in this one, I added a flag for storage access modes. And this had to do with, originally when I was starting work on this, one cluster had storage that was read-write many, and on the destination cluster, I needed it to be read-write once because that was the only storage that was available. So that was one of the things that had to change. You see here that I manually added the security context, but that was, fortunately, the CraneLib libraries actually supported some of these mutations already, and so it was just this simple. The important thing that we have to think about going forward is how we expose this to the user in a way that they can easily manage on their own. The other tab, let me see if I can show you one of the others. It's not easy to just switch between tabs without. Yeah, the other one that was interesting was the changes in CraneLib. So a lot of what had to happen here was some updates to deal with some of the default resources that are created in a cluster. And for example, stripping the default RBAC in the CA bundle. What happened here was one of the things that we learned from the exercise was that there are things that are cluster specific, and that there are some flags that we can allow multiple plugins to use those flags, and they can determine how to handle those flags based on their needs. So in our specific example, the strip default RBAC in a Kubernetes cluster, that could just mean the default service account. That doesn't need to be migrated. But in an OpenShift cluster, that could also mean the builder and deployer service accounts. So there are a lot of lessons learned. I included the link to the GitHub issue that summarizes the research done and has links that we can talk about. So that's all I have. Any questions? Go for it.
Yeah. Can you please share the security context of the pod stuff that we talked about?
You want to see it, like you want to look at it?
Yeah. Okay, I don't care actually. I just saw it on the screen. So there are like new capabilities that are added to the async pod. Are they gonna? So I was talking about the transfer PVC subcommand, the changes in Crane, not the CraneLib. So basically, to force the right SCC, you had to add a few capabilities.
Yeah, that's right. I wish it would actually show me.
So what SCC is that on OpenShift? Is that, so my concern is around the non-active stuff.
It was the SCC was the KubeVirt controller.
Oh, okay.
So, oh yeah, that's actually a good point. Was that this is the one we're talking about, right? I don't know why I'm having trouble getting it to show the right tab. Maybe if I just close the wrong one, then I won't be able to pick it up. But yeah, that was actually one of the things that we learned was that you needed, in some cases, in the case of a virtual machine, you couldn't be just a generic user.
Right. Okay.
And perform this work.
Okay. Yeah, that explains it.
Yeah, I think the lesson is I have too many tabs open. Sorry.
I think Alay had a question too.
I was just trying to explain while David finds out his tab. But KubeVirt creates an SCC that all virtual machines write data to. And the interesting thing there is KubeVirt doesn't care much about GID and UID. It cares more about SE Linux labels.
Yeah. Right.
So this KubeVirt SCC adds custom SE Linux labels that we need to make sure is present on the rsync client pods. And we need to accept rsync pods using that SCC. So anyone who wants to migrate or transfer PVC would have to be blessed by the admin to use that specific SCC that KubeVirt creates.
Okay. So ideally, we would have this as an option in transfer PVC command, like use this for, like, I'm using this for a VM.
Yes. So what I was thinking was that we would have two optional flags: pod security context and container security context that would take a JSON and then mutate our sync pods.
Oh, I see.
Accordingly. Yeah.
Okay. Cool.
Cool. Thank you, David. Good stuff. Okay, just before we wrap up, I just want to see if I had hopefully screen sharing. I don't know if it is. Anyway, I just want to let everyone know that the next meeting is a month from now, June 29th. As of right now, no topics are identified. But if you have anything that you would like to share, please let me know and we'll add it on. And I will have this posted to YouTube later on today. Thanks everyone for attending.